In the 3rd century BC, Archimedes proved the area formula for a circle. His method harnessed the power of infinity in a way that would set the stage for calculus to emerge nearly 2,000 years later, but it also revealed a paradox at the heart of math that wasn't addressed rigorously until the 1800s. Archimedes was the greatest mathematical thinker of his time and among the most important mathematicians of all time. In addition to writing a number of books that expanded the ancient Greek understanding of geometry, he was a powerful inventor, creating the first compound pulleys as well as a type of water pump that is still in use today. Archimedes was so passionate about math that he would often forget to bathe and eat. He died at the tip of a sword when he refused an invading Roman soldier's orders because he was too engrossed in a math problem. But more on that later. So, what was so special about circles anyway? To answer that, let's start with rectangles. It's pretty easy to see how we can divide this rectangle into little squares on a grid and multiply length by width to find the area. But when we try to do the same thing with a circle, the diagram's a complete mess. The circle doesn't line up with the grid no matter what we do. Back in Archimedes' time, mathematicians and philosophers were already wrestling with this problem. They were fine with areas of shapes that had straight lines, like rectangles and triangles, but working with circles and curves was not as simple. There's some disagreement here about who knew what when, but it seems like Eudoxus of Cnidus had shown that the area of a circle was proportional to the square of the radius over 100 years before Archimedes, and Euclid knew that all circles are similar regardless of size. But Archimedes is credited with identifying pi as we know it today and with proving the area formula for a circle.
To understand the thinking behind Archimedes' proof of the area formula for a circle,
let's start by dividing a circle into 4 pieces like we're slicing a pizza. Now notice that the circumference has also been split in 4. So if we rearrange these into an interlocking shape, we can see that there are 2 slices pointing up and 2 slices pointing down, so the distance across both the top and the bottom parts of this shape is half the total circumference. Using modern notation, we'd say that this is equal to pi times the radius. Meanwhile, the other sides are equal to the length of the radius, and we can make those vertical by cutting one of the slices in half and moving it to the other side like that. Now this shape doesn't really look like anything familiar yet though, so let's